Alright, we're now to the ideal gas law. Alright, everything changes up a little bit in ideal gas laws. With the ideal gas law, we are not looking at a starting and an ending temperature, or starting and ending volume, or a starting and ending pressure. We're not doing anything to it. Alright, what combined gas law looks at is we have a gas-filled container and we look at it at that point in time and find out information on it. So, the ideal gas law describes the physical behavior of ideal gases in terms of pressure, volume, temperature, and, we're adding something new here, the number of moles. Yes, moles comes back. Alright, so here we go. We started the semester with moles. We're going to end it with moles. So, our equation for it is PV equals nRT. Oftentimes you'll hear this as PivNert. Alright, so for people to remember it, PV equals nRT. So, let's go through it. P is pressure. V is volume. I'm going to jump over to T, and that's temperature. These are the ones we've dealt with. So, pressure, volume, temperature. Don't forget temperature. Yep, still must be in Kelvin. Alright, let's talk about the N and the R. The N represents the number of moles. So, N represents the number of moles of your gas. And R, alright, R is the ideal gas constant. R is the ideal gas constant. This is a constant. Depending on your units you use, the number can change, so look carefully at your units. We're just going to write down R as this, 0.0821 liters atmospheres per mole Kelvin. Yes, this whole thing here is one old big unit for it, okay? Liters atmospheres per mole Kelvin. Alright, so with all that being said, I'll show you how to use PivNert. And, alright, calculate the number of moles of gas contained in a 3.0 liter vessel at 3.00 times 10 to the second Kelvin. So 300 Kelvin, with a pressure of 1.50 atmospheres. So, PV equals nRT. Right? PV equals nRT. So, were we given the pressure? Absolutely. There it is. 1.50 atmospheres. Times, were we given a volume? We were. 3.0 liters. Is equal to, were we given N the number of moles? No, it says calculate the number of moles, so we don't know N. Alright, we're not given R, but I will give it to you every time. You don't have to memorize it. So 0.821, 0.0821 liters atmospheres per mole Kelvin times 300 point Kelvin. So exactly 300 Kelvin. Alright, you got to solve for N, so manipulate this equation. If I divide by all of this fun stuff over here, going to cancel out, leaving N by itself, so I must do it to the other side as well. N is equal to, we can plug it in our calculators. 1.5 times 3 divided by 0.0821 times 300. Our N turns out to be, let's see, with 2 sig figs, 1.8. Let's see what units are left. Atmospheres and atmospheres cancel. Liters and liters cancel. Kelvin and Kelvin cancel. We are left with moles, which is what we want. So whatever this gas is, we have 0.18 moles of it. Right? What's also going to be asked of you is something like how many grams. If that's the case, then I would have to give you what the chemical is, like carbon dioxide, and then you would have to convert from moles to grams. There's lots of things we can do with this, including some fun stoichiometry problems. Right? One other thing to remember is we did this at the very beginning of stoichiometry, or around stoichiometry, and that's when if you have exactly 1 mole of a gas at STP. So go back over STP. STP stands for standard temperature and pressure. All right, standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. So at STP, 1 mole of any gas takes up 22.4 liters. All right, remember that 1 mole of any gas takes up 22.4 liters. All right, good luck to you.